brown thing's the ribosome, the red thing's the messenger RNA.
Making the amino acid.
The thing you see in this teal green, there's another kind of RNA, right? We're only beginning to talk about this stuff, but there's the growing what? What do I know this amino acid has to be right here? That's methionine. Always the what? It's always the first one, because the first triplet, whatever it was back here, said what? Methionine, right? AUG. There we go. I'm giving you a copy of this handout, this transparency. This is all about point mutations. What do we mean by point mutation? It's a mutation at a single what? A single point in the DNA. You get it? A point, 1 point, single mutation. They're called micro mutations. What does micro mean? Small, right? One nucleotide. You get it? One nucleotide. Well, that's a micro mutation. What's a macro mutation? Macro means big, like somebody having an extra chromosome, correct? Would you agree that that's not a micro mutation? That's a macro mutation, right? There's a 3 or 4 there. Three. People with Down syndrome, for example, they have an extra copy of what? Chromosome number 21. Well, that's not a micro mutation. That is a huge mutation. You get it having a whole extra chromosome. That's not what we're talking about here. We're talking about micro, tiny little mutations where I have messed up only one what? One nucleotide. Are you with me here, everybody? Micro mutation, right? And there are different kinds, as you can see. Now, what you see at the top in blue, blue is always the DNA, the red is the what? The RNA, and the purple blocks, those are my amino acids. You get your bearings here? Of course, you don't have color on yours, right? Although you could use highlighters to color them. What do we mean by the wild type? That's the normal DNA, no mutation, right? No screw up. That's what we mean by the wild is the natural, right? It's the way it's supposed to be, right? Now, what I want you to look is over here. There's the mutation in yellow. Again, this is why you don't have the colored version, would be nice. But notice what's supposed to be right here, everybody. This is supposed to be CC what right here?
G.
CCG. Did everybody say it? CCG. And we have a mutation that says CC what?
A.
CCA. Now, when we convert that to RNA, this would code for what? If that's CCG, that's going to be GG what? GGC, which codes for what amino acid? Glycine. Look it up, GGC, right? GGC, there it is, glycine. Now, here's the mutation. Instead of having CCG, I got CCA, and so what does the RNA look like? GGT. Well, look up GGT, right? Well, you have to convert it to RNA, and you're going to get GG what? GGU, and isn't it nice that GGU, just by chance, happens to also code for what? Glycine. So let me ask you this question, critical thinking. Critical thinking, I ask you to do this every single day of this class. Will this mutation have any effect on the protein?
No.
Of course not. It's the same what? Same. Now, is it a mutation? Let me ask you this question. Has there been a mutation? Yes, because have we changed the nucleotide sequence of the DNA? Absolutely. So there is a mutation. But does it affect the protein? No way. Because it just happens to be that that mutation does not change the amino acids. Because there were synonyms, you see, because there were synonyms in the genetic code, do you see that some mutations would have absolutely what effect? None. Do you get it? That kind of mutation, and you see it right here, it's called a what mutation?
Silent.
It's called a silent mutation because it doesn't have any effect on the organism. Do you agree? It's the same amino acid. Nothing's changed. Are you with me so far? So, you know, at least there's such a thing as a silent mutation, meaning that it has no what? No effect. It doesn't change the protein in any way. The protein's shape is going to be the same. The protein's function is going to be the same. Are you with me? Now, let's look at this one. This time, over here we have TCG, right? What was the original? It was CCG. Now we have TCG, which means the RNA is now what? AGC. And AGC calls for what? It calls for serine. Well, now, did I change the amino acid? I did. Now, look on your sheet of the 20 amino acids and tell me whether you think this might have a lot of impact or maybe not so much impact. You can make that decision if you use good critical thinking skills. Look up your 20 amino acids. We have switched what for what? We switched glycine for serine. Glycine is what kind?
It's a hydro.
Is a hydrophobic, but serine is hydro. So is it likely that this one's going to have a pretty dramatic impact? Yes. Because one likes water and one doesn't. Could it really distort the shape of the protein? You see my point? What if, just for the sake of discussion, instead of glycine, we went to alanine? We went from glycine to alanine. It could have an impact, but there's a good chance that maybe it won't change the shape very much. Why? Because they both what? They're both are hydrophobic, right? You get what I'm? You see how the kind of mutation can have a lot of impact on the shape of the protein. What I'm trying to get you to see is, are all mutations the same? Is the point of discussion? No. Some mutations are completely what? Silent. Right? Others can have a serious effect. Right? Now, this type of mutation, listen carefully because this vocabulary is going to really start to confuse you. This is called a missense. This one was called a what mutation? This was a silent one. This one's called a missense mutation. Now listen to this. Don't try to write it, listen to it. Missense still makes sense, it just makes different sense. Let me hear that again. Missense still makes sense, it just makes different sense. You get it? In other words, AGC, does it still code for an amino acid? And if I'm the ribosome, I'm reading that, does that make sense to me? Well, of course it does, but it's the wrong sense, you get it? It's a missense mutation. In other words, I have the wrong amino acid. You get what I mean by a missense mutation? A different amino acid has been put in place. That's missense. It still makes sense. It's just different sense. Am I making sense? Yes?
Yes.
Because look at the last one. This one is what? This one's nonsense. Nonsense doesn't make any sense. Missense makes sense, just different sense. Nonsense makes no sense. Am I making sense? You followed that and said, I know what the hell he's talking about. I think you're as surprised as I am. So I understand what the hell he just said, right? Nonsense doesn't make sense. Missense makes sense. It just makes different sense. Now, how do I know when I get a nonsense one? I get a premature what? Stop. I mean, I was just starting to build my what? I was just starting to build this protein, and a freak mutation actually put by accident a what? Triplet there, one of the three whats? Look up UAG, and UAG is one of the whats? It's one of the stops. Wow. We've only just started building the what? The protein. That's what we mean by a nonsense mutation. Let me repeat what a nonsense mutation is. It's when you have a premature stop. What do I mean by premature? We weren't finished building the what? The protein, and all of a sudden the ribosome gets to a stop that shouldn't be there. You get it? Are you all with me? Now, what I need for you to see is that both silent, missense, and nonsense, they were all the result of a single what?
Nucleotide.
Of a one substitution. All we did was substitute one nucleotide. You get it? That's the substitute, right? One nucleotide substitution. Because the other side is different. Right? Here I was only substituting, right? Here I'm not substituting. I'm either I'm adding an extra nucleotide, or I'm what? Taking one out. Now, who can tell me a good critical thinking question again? Why are these always going to have very, very, very serious ramifications? Yeah.
You won't have triplets, so
You'll still have triplets, but every triplet will have been what? Thrown off. Right? That's called, listen to what it's called. It's called a frame shift mutation. It's called a frame, look at it, it's right here. It's called a frame shift mutation. Does everybody follow this? Because I'm not sure everybody does. Look. Here was my DNA, right? And here's my first triplet. Here's the second triplet. there's the third triplet, there's the fourth triplet, the fifth, and on. You get it, everybody? Now, if it's a substitution, all I did was I took that one out and I put a different nucleotide there. But all the other triplets are still completely intact, yes? But if I have an insertion, in other words, we added another nucleotide, well, now look what happens. That becomes the next triplet. That's the next one. That, you see how they're all going to be different? Is that going to screw up my protein big time?
Yeah.
Absolutely. You get it? Now, does it matter whether I insert or delete? Will the same thing happen? You see what I mean? If I inserted, I added an extra nucleotide. Well, that screwed up every codon after that. The same thing would be happening if I did what by mistake also, if we lost one. Now, this becomes the next what? Codon. There's the next codon. Do you see how they're all messed up? Do you see that frame shift mutations are going to have much, 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 much more serious consequences? Unless I lost a whole what? Maybe I deleted an entire what? Triplet. At least that doesn't create... You see the difference this time? In other words, if I just lost that whole triplet, well, at least every other triplet has stayed the same. You get my point? All I'm trying to get you to see here is that not all mutations are the same, are they?
No.
They go all the way from having absolutely no effect at all, correct? To completely screwing up the what? The protein. You get it? I mean, a frame shift mutation, is that going to screw up a protein big time? Would you create anything that even functionally resembles what that protein is supposed to be like? Absolutely not. Now, what if that is absolutely a protein you need for survival? What's going to happen to this very, very, very young embryo, probably within the first weeks of development? It's going to die. I mean, if you need this functioning protein and the mutation has screwed it up so bad, and so the woman would experience what's called a miscarriage, right? And of course, these are really sad things, right? I mean, it's, especially if it's the couple's first child, you know, they're really looking forward to having their first baby, and all of a sudden, you know, in the first or second month, she has a miscarriage. Now, that may be a tragedy, but you understand that probably happened because there was something very seriously what? There could be something very, very seriously wrong with that embryo. I mean, this is not a frame shift mutation like that. You understand, you got a pretty badly screwed up what? Protein, and if you need that protein to survive, that's what caused the miscarriage. Making sense there? You want to see how a little bit of biology, you see how just in 2 class days, it's like, wow, there's so much I understand now about what can cause mutations, and what the hell a mutation really is, and how some mutations really could be completely, had no effect, silent mutations, but others can have extremely, extremely significant effect. And that all comes from just 2 days of biology. Yes? You understand a great deal more about the world in which you live. Right? I mean, I'm sure you all started hearing about DNA and RNA somewhere in 3rd and 4th grade, but it's not until you see this and say, oh, so now I know what the hell all this is about. Now I know what DNA does, right? How it makes these proteins, and then proteins in turn do virtually what?
Everything.
They do everything. Wouldn't it be interesting to have this kind of a critical thinking question on a test or a quiz that said, make the argument for whether you think nucleic acids are more important than proteins, or proteins more important than nucleic acids? How's that going to go? Molly?
Without nucleic acids, there would be proteins.
So you're making the case that, as far as you're concerned, the nucleic acids are more important. Because what her argument is that, well, without nucleic acids, I can't build a what?
Protein.
I can't build a protein. On the other hand, who does everything?
Protein.
Proteins do everything. So one could say, well,
Can you choose both?
can you choose both? It's just that I won't ask you the question, but it is one of those things that it's interesting to ponder, right? I mean, I really, the truth of the matter is I can't have one without the other, right?
Can we make a third argument and say that RNA is more important?
No, you can't. Because the question was, is it nucleic acid or is it protein? Sie verstehen, ja? Vous comprenez, oui? And for you monolingual barbarians, I asked you in German and then in French if you understand that.